Hello everyone, welcome back to this 8th tutorial in my statistical analysis in Python series, and we are currently focused on correlation analysis, learning about correlation analysis. In the last tutorial we started with the basics where we understood what Pearson and Spearman's correlations are, and in this tutorial we're going to focus on partial correlation. I'll explain what that is in a minute. And there are two other parts that are coming, in the next few weeks on this specific topic of correlation analysis. And again, if this is of interest to you, in general, if statistical analysis in Python is of interest to you, you should consider subscribing to this channel. Hit the pause button right now, find the subscribe button, and while you're there, find the little thanks button if you're feeling extra generous. Okay, so what are we going to cover here? Well, completely about partial correlation. So we did look at Pearson correlation for linear relationships and also Spearman's rank correlation for monotonic relationships. And Spearman's is used when certain rules are broken, where Pearson is probably not appropriate. Again, a quick summary of last tutorial. And now we are going to look at partial correlation, and the other stuff comes in the next couple of tutorials. Now, first, let's understand what partial correlation is. And I promise this is the only slide we're going to look at before jumping into the code. Okay, because obviously we need to understand some background, although I did include a lot of notes in the Colab notebook itself. Okay, the purpose of partial correlation is to control for the influence of one or more confounding variables when examining relationship between two primary variables. So you have two variables, one goes up, the other one goes up. We know, okay, they're correlated or negatively correlated. One goes up, the other one goes down. Either way, they're correlated. Now the question is that correlation actually true, or is that actually controlled by a third variable that we are not even considering in this correlation? So coming to our example, like a practical example, the question is, are bill length and body mass correlated for in our penguins? The confounder is basically this third variable, confounding variable, like species, for example. So maybe these are correlated because of the species, right? So larger species might have both longer bills and higher mass, right? So in that case, then it looks like it's correlated, but maybe it's not. So the solution is basically, hey, calculate partial correlation, controlling for species, which basically means, in a way, you remove the effect of this species. You kind of remove that and look at what's remaining and see if it's still correlating. That's basically what partial correlation is. And if you look at the equation right there, x and y are these variables and z is the confounding variable, right? And it's kind of straightforward, actually. This is the partial correlation between your x and y, two variables, while controlling for z. And the top in the numerator, you have Pearson correlation between x and y. We learned that in the last tutorial. This is between x and z, and this is y and z. Once you calculate these, then you can kind of calculate this effect right there. I think that's what I mentioned down here under interpretation. It's R basically gives you the correlation between x and y while controlling for z. Okay, so I think we are kind of ready with that background to jump into our code. So here is the Colab notebook from our last tutorial. This is exactly where we ended, and this is a continuation of this because we're working on the same data set. And here is where we ended. What does this mean? Well, we ended by plotting our Pearson R value against the Spearman rho value. So we calculated both correlations, Pearson and Spearman, on our data, and then they kind of fall on a straight line that tells us there isn't much difference between the R and the rho values, even though our data kind of violated a couple of rules. Like for Pearson, it has to be, both variables needed to be normally distributed, for example, and they were not normally distributed. But then they're kind of close to normal distribution, which is why there is a decent agreement between Pearson and Spearman. Okay, watch the last tutorial if you want to get better context of that. But right now, let's go ahead and understand what partial correlation is. And I should warn you that certain aspects, I should say, I repeated multiple times because I learned that way. I am dumb enough not to pick up topics on the first try. After the second try, I understand a bit more. And the third try, probably a bit more. And I bet some of you are like me, where repetition definitely helps. So I tend to repeat some of these. Apologize in advance. Okay, so what is partial correlation? We talked about it. So repetition number 2, it's basically the relationship between two variables while controlling for the influence of one or more other variables, right? So it answers the question, basically, what would the correlation be if we held the confounding variable constant? This is third variable that we suspect is the reason why these two are correlating, is what we call the confounding variable, right? So here's the mathematical formula, although you saw that in the PowerPoint presentation, but we will not be using this formula directly, primarily because this does one variable at a time, as you can see. For example, if you have 3 different species, like if Z is species value, right? So if you have 3 different species, then you have 3 different Z's that you need to calculate. Which is okay, but I just want to highlight that point right there. Now, when to use partial correlations, we already know. When we suspect that a third variable might explain the relationship between X and Y, this is when we use partial correlation. So when it comes to our penguin data set, for example, we look at bill length and body mass. Simple correlation, fine. When I say simple correlation, that means Pearson or Spearman's. Let's stick with Pearson's correlation because these are continuous variables, and let's assume they're normal. So, okay, Pearson correlation, bill length versus body mass, positive. Okay, you have a strong positive relationship or correlation, let's say, between these two. But if you think about the species, larger species have longer bills and higher mass. So the question is, so is the species actually kind of affecting this relationship? This is exactly when we remove or account for the species differences and look at the residuals and see if the residuals are still correlating. This is literally the approach that we're going to follow in our code right now. I repeated what is partial correlation again, part repetition right there. I repeated this because I took so much notes thinking about how to explain this to the audience, and I threw all the notes at ChatGPT and said, okay, go ahead and organize it. It organized it, and apparently I took this multiple times because when I take notes, I don't know if I have already talked about it, and then I kind of copied and pasted the notes. But I bet you'll learn something by reading all the notes here. Okay, so why is partial correlation important? Again, confounding variables can create misleading correlations. So it allows us to actually quantify that effect or account for that effect. Now, the mathematical intuition itself, I think we talked about this. How much do X and Y vary together, right? So if you only look at simple correlation or Pearson's correlation, then it's just correlation between X and Y. You ignore everything else. You just take these two arrays and then you compare them and say, okay, how is the correlation? Now, partial correlation is obviously pretty much the same, except you are removing the influence of Z. Let's park that topic there. Well, not park. Let's actually skip this part about the formula because we are going to use the first method here in our code. And what is that first method talking about? Well, this is called regression residuals approach. This is the most intuitive approach because let's say you have X and Y, two variables that we are obviously trying to quantify the correlation. And we suspect that there is a third variable, Z, that is controlling these two, which basically means X is probably a function of Z, same as Y is probably a function of Z. If so, well, let's go ahead and fit a linear equation of X as a function of Z. Similarly, linear equation of Y as a function of Z. When you do that, you get, and with your data, you get a linear equation formula, obviously. Then you get the residuals, which is nothing but the error, right, of each data point in your X minus whatever the data point on that linear regression line is. We call that X predicted. Yeah. In other words, you have the equation there, plug in the Z value for that linear equation and get the X value, which is your predicted value, and you get the residuals. You do the same for Y. This tells you if there is a relationship between X and Z, then the linear equation, if it's a strong linear equation, then by subtracting that x minus x predicted, you should get very smaller residuals, right? So basically at the end of the day, you have residuals here, x residuals, and residuals for your y. Now what do you do with these two? The core question is x and y correlated? So go ahead and do the Pearson correlation between x residuals and y residuals. Basically removing the effect of z from both of these, and then you're looking at the correlation. This is your R. I hope that makes sense. This is the most intuitive. When I looked at this, it made the most sense. I hope it does to you too. And direct formula is where you saw the formula, you plug in the values, and I have the formula as part of the code, and it only works if you have one confounding variable. Again, when I say only one confounding variable, for example, the z is species. Within the species, we have 3 different species in our data set. So we have 3 of these for species right there. It's not just one, right? So that's what I mean right there. Okay, so before jumping into actually applying the partial correlation on our penguin data, I just want to apply this onto a synthetic data so we understand, again, we build this intuition further about what partial correlation is doing right there. To do that, we're going to look at 3 separate scenarios. One is truly confounding, where both x and y are only related via z. They don't have direct relationship, x to y. The second scenario is there is some relationship between x and y, but they're truly also confounded by z. The third one is x and y are, z is acting as a suppressor, which means it's suppressing the true relationship between x and y. So in other words, x and y actually has a good, strong relationship and not related through z. That's basically the 3 scenarios. And how do we synthetically generate these 3 scenarios? Well, in one case, we're generating 200 data points, by the way, for each. And in one case, we only have x as a function of z. All the x data points that we are generating, obviously, we have some random values from normal distribution right there. But x is related to z. Y is also related to z. You see, there is no other relationship. X is not related to y here. They're only related to z. That's our scenario 1. Okay? In scenario 2, x is related to z and y is related to z, but also a little bit on x. You can see how these are correlated, right? So x is correlated with z, okay? It's a function of z. Y is also a function of z, but it also has a correlation with x. This is how we are defining how y is correlated on x. And in scenario 3, as you can imagine, our x is right there and z is actually depends on x and y is actually depending. So it's z suppresses the true xy relationship. So I lied when I said earlier when I said they're not dependent on z and z is not in the picture. Here what I wanted to show is that z suppresses the true xy relationship. So x is right there. You're generating some values for x and then we are saying z is a function of x, but y is also a function of x. Okay? And we have z also a function of, y is also a function of z right there. So basically y depends positively on x, but then negatively on z. So whatever the correlation is between y and x, z is subtracting that. That's basically the scenario right there. Okay, let's go ahead and run this cell and look at the results. And rest of the code is maybe I should go through scenario 1, scenario 2, scenario 3, and these are the 3 scenarios, and this is all plotting. So we are calculating the Pearson between each of these xy partial correlation manually, x, z, y, z, and we are actually plugging that into this equation. We calculated numerator, we calculate denominator, and we are just numerator over denominator is our partial correlation. So basically the equation I'm just plugging in the values into the equation. And if you remember, the equation is nothing but you have Pearson for xy, Pearson for yz, xz, and all that, and you plug those into the equation. That's exactly what's going on here. And then we are just plotting these partial correlation and the scatter plots. So let's go down and have a quick look at the results and then jump into our Penguin data. Okay, so the truly confounding simple correlation gave us 0.498. This is just Pearson between x and y without accounting for any z. So it tells us, oh, there's a good relationship, strong relationship or correlation between x and y, 0.498. But then once you remove the effect of z, the partial correlation value is 0.02, like almost zero right there, right? So typically, we look at the difference between simple and partial correlation, and then that's a strong difference. Basically, the interpretation is x and y are only related through z. In case of partial correlation, the simple correlation gave us 0.769. Obviously, there is a correlation between x and y. The partial correlation gave us 0.515. That means, again, when you take the difference, x and y have both direct and indirect relationships. That's basically what we infer from here. And the suppressor variable, no wonder we got negative value right there. Basically, it tells us z suppresses the true xy relationship in this case. So these are the plots. You can see the truly confounding. So it looks like, I mean, these are all the data points, x and y, related only through z. And the simple and partial values. I mean, we just discussed the results. I'm not sure if it's worth looking at the plots. So the one thing that we need to look for is in the strong confounding case, if you plot x residuals and y residuals, there is no basically relationship right there, right? And in this case, there is a strong relationship right there between x residuals and y residuals. That's, I think, the only thing that's worth noting from these plots. Okay, now let's go ahead and, I mean, I added explanation of how to interpret the simulated results, but obviously in this video, I talked about it, but when you look at the notebook, you have the explanation right there. Now, let's calculate partial correlation for our actual, Penguin data. And again, I explained all of this I just talked about, right? So we are going to use method 1, and this is the function that contains this method, both methods. And method 1 is using linear regression to predict each variable from the control variables and calculates the correlation between the leftover residuals. So like we just talked. So we are going to predict x using control variable. This is nothing but fitting x to z, fitting y to z, and then calculate the correlation between the residuals. We just did that earlier. Method 2 is the direct formula. We're not going to use that. And this is something I think I should mention. There is a helper function that you'll see to create dummy variables. What does that mean? Well, our species, actually, it's an actual real name, right? So Adelie, Chinstrap, and Gentoo are the 3 species that we have, and these are actual names. So we need to convert that into some sort of one-hot encoding method. So that's basically what this create dummy variables is, helper function. So we convert these into numerical variables, and it uses one-hot encoding, and we use drop first equals to true to avoid multicollinearity. What the heck does that even mean? I'll talk about that in a second. And then we perform the main analysis, like by calling this function onto, again, we'll look at that in a minute. Okay. So I thought I added notes, or did I do that in my mind about this create dummy variables? If it's not there, I'll explain that in a second, but let's keep scrolling. I may have written that anywhere, somewhere. And some rules of thumb that I just put: greater than 0.2, species is major confounder, and less than 0.1, relationship exists largely within the species, right? And then there is also another function I just added to perform within species correlation. So you only look at one specific species, and you look at all the x and y values for these 2 variables, right? And then look at the correlation within the species, just for the fun of it. So you get an intuition in terms of how the data is within the species and across the species. Okay. Oh yeah, I did put additional notes, thank God. Otherwise, I almost opened my notepad where I took notes about explaining this. So why only two dummy variables for three species? In fact, when you look at the code, you will see drop first equals to true. That means when we have Adelie, Chinstrap, and Gentoo, it's going to drop the first one and only encode these two. Why? I had this question initially, that's why I put that here. This is about avoiding multi-collinearity problem in regression. If you know that, great, move on. If not, well, here is the explanation. When you have three categories, right? In our case, Adelie, Chinstrap, and Gentoo, you only need two dummy variables. And the dummy variables, let's say when you convert that, it may look like this: 0, 1, 0, 0, 0, 1. In other words, it's a value of 1 if it is Chinstrap. It's a value of 1 if it's Gentoo, otherwise 0 in this form of encoding or text right there. So with this, you can identify all the three scenarios. Basically, think of this almost as 1, 0, 0 is our Adelie. Okay, that's what drop first actually does. For Chinstrap and Gentoo, it looks like this. Now, why not just use three dummy variables? Why confuse all of this? Why not just put 1, 0, 0 as our Adelie, and then for the others 0, 1, 0, 0, 0, 1? Well, when you add all the three, if you do the three dummy variables, then you will end up with 1 always. When you add them, you always end up with 1. This creates multi-collinearity because the three variables are perfectly correlated. It breaks the regression calculations. That's basically what this multi-collinearity is. So the dropped category, Adelie, becomes the reference group, the way we handle it. That is the reference group, and the regression coefficients tell you how these other two, Chinstrap and Gentoo, differ from this Adelie. I hope that makes sense. That's why we are dropping this. Okay, and that's why we are encoding only the other two, or creating dummies, let's say, get dummies for the other two by dropping the first. This is the common process when it comes to partial correlation. Okay, now let's go ahead and run this and look at the code. While it's running, it's already done. But what are we doing here? Again, method 1 is what we need to look at using regression residuals. You have the X controls and X target. Right? So these are the control variables. These are the target variables, which is basically our X and Y's. And these are the control variables. Think of this as Z, right? In our XYZ. And now we are going to fit a linear regression model between what? Between your X controls and the target. Okay? So you're going to fit a linear regression. And then for X values, you're going to look at your target minus the prediction. I hope that makes sense. We looked at this once. This is the second time we are looking at it. And similarly, we do the same for Y. X is variable 1, Y is variable 2. So you do this for each of these variables. And then the step number 3 is nothing but your Pearson R value by using the residuals only, because we accounted for the control variables in the linear equation and only looking at the residuals. That's it. And we're printing it out. And method 2 we are not following, but if you want to, here is the equation. It's going to skip this because our length of control variables is not 1, it's going to be 3. We have 3 species. Okay, and anything else worth mentioning? Create dummy variables. And Pandas itself actually has this method called getDummies, so it does create the variables. So go ahead and we will be using that as part of our analyze species effects. This is the main function that brings everything together. And our first thing is create dummy variables for our species dummies, and that's what we're going to use as part of our analysis. Okay, we are obviously looking at these different relationships. And anything else to talk about? Again, we're calculating Pearson R between the clean pair data and then the X variable and Y variable. And this is the simple correlation. In simple correlation, we are not accounting for the third variable, right? So first we are calculating the simple R values and P values, and then here we are calculating the partial correlation, not just a simple correlation, with the control, which means we need to provide the control variables right there, and it's going to give us our partial correlation result. And then we are going to look at the difference between the simple and the partial, just for the fun of it, and go ahead and print it out. And if the difference is above 0.2, then we say, okay, there is a large effect of the species. Otherwise, there is a small effect. I think that's pretty much it. And the next part would be perform within species correlations. And again, this is basically for each species. Go ahead and look at the correlation right there. That's it. Okay, so we already ran this part of the code, and let's look at the results and stop this tutorial and then continue in the next one. Again, please do not forget to subscribe, but let's look at a couple of these results. Okay, so the dummy variables are created for Chinstrap and Gentoo. The other one becomes this reference species, and now we are looking at bill length and body mass. How are they correlated? Well, the X variable is bill length, Y variable is body mass, and controlling for Chinstrap and Gentoo. Okay, now regression, residual approach. That's the only approach we are doing. The partial correlation is whatever that value is, 0.58. That's a good correlation, right? And the p-value is much less than 0.60. So statistically, that is a valid statistic. That's what we mean, which means the null hypothesis has been disproved. And we did the significance test. The summary is the simple correlation 0.5895, partial correlation 0.5823. Remember, we look at the difference. The difference is 0.0072, very small difference. That basically tells us the relationship is largely within species, so there is no species effect right there. One more, flipper length and body mass. Let's completely scroll down here and see. The simple correlation gives us 0.87, partial correlation gives us 0.588, and the difference is 0.2850, and species is a confounder there. In fact, it was a decent confounder. 0.28 is larger than 0.2, so we said, okay, that's a significant effect, so it's a major confounder. Go ahead and look at all the other ones right there, and we should see some plots. And what do we see in the plots? In fact, if you look at this one, this is where it says it's a major confounder, right? Bill length and bill depth. You see that the three species, the data is not uniformly distributed. You can see that all the values for bill length and bill depth are clustered down here. For these, they're clustered up here. For the Chinstrap and for Gentoo, they're down here. So it's almost like you can run a k-means algorithm on this and classify the species. So that basically tells us that there is a strong effect of the species on this correlation between bill depth and bill length. And same with, you can kind of see that in most of these, actually. Some effect, except here it seems to be not as much. And the bottom plot is basically the residuals. Yeah, so bill length and body mass residuals, you see a nice straight line right there, straight line here, kind of a line right there. But delta R, the difference between the both is pretty significant, so a strong effect right there. And within species correlations, again, this is within each species, and I think I have a summary of each of these, down here. Visually, you can see for Adelie and Chinstrap and Gentoo what the correlations are right here, and in fact, you can compare them if you want to compare these. So all this, why did I do this in species? You put this together with the partial correlation values to actually make certain decisions on your specific data. Okay, and I added some of the summary down there, and I think this is the last. There are certain biological insights I kind of added. For example, the body size relationships are real, right? We see a strong effect right there. So bill length and body mass correlate strongly with the species. That's one thing that we saw earlier. That means this suggests genuine biological scaling. Bigger individuals, bigger penguins have proportionally longer bills. You would think that's a no-brainer, but obviously this is a scientific finding right here. So you have to look at all the, statistical results and then make that decision not based on your intuition only. Okay, so in the next tutorial, let's look at a few advanced topics, and the one after that is going to be correlation versus causation. So please do subscribe if you haven't already done so. Thank you very much for your patience, for sticking all the way until the end of this long tutorial. Thank you.